Okay, so let's begin a new chapter where we talk about some really neat physics, that physics being electromagnetic induction. And basically what we're going to try to master, the topics we need to master here in this chapter are Faraday's law, okay, and how it relates to an induced EMF, which is simply a voltage in a loop of wire, okay, and how the change in magnetic flux relates to that as well. We're going to determine, using another right-hand rule, the direction of the induced EMF using Lenz's law, and how the EMF is actually a circulating electric field. So how the circulating electric field relates to the change in flux. We won't spend too much time on the last few sections of this chapter where we go over Maxwell's equations. I will talk about it because it's really cool, but I won't be testing on it. And finally, we won't really have any time to talk about superconductors. Unfortunately, if you're interested, you can certainly meet with me and we can talk all about superconductors. I'm not an expert, but I know a little bit. So let me motivate this topic for you. Electromagnetic induction. Where does it come into play? How does it involve us in our everyday life? Well, one of many important applications of electromagnetic induction is how we used to transmit information from a credit card to a machine that you're using, to pay for things. Although, a lot of people probably still do swipe their cards. Nowadays, we have a chip card, all right? It has a little gold chip on it. Looks something like this, all right? That's different technology than what I'm talking about right now. What I'm talking about is sliding your card in and out of a slot, okay? And specifically making sure that this magnetic stripe is, doing its job. So what we're doing is this magnetic stripe on the back of your card, we're waving it in and out of a machine. And what's happening when we do that? Well, we're actually changing the magnetic flux near that reader, okay? So a card reader at a gas station is basically operating on magnetic flux. So this change in magnetic flux is creating a voltage, which creates a current, and the information from your card is transmitted to the machine. So we're going to basically be breaking apart that phenomenon using Faraday's law and Lenz's law, okay? So as always, when we start a new topic, we're going to discuss the experimental observations of this new phenomenon. So way back in the 1800s, there were some experiments done, and one of those experiments involved a magnet and a loop of wire that is able to carry current, so maybe copper or some other material, okay? A loop of current carrying wire. But as you can see here with this machine is called a galvanometer, which measures current. As you can see, if we just hold a magnet above this, this is just called a solenoid. Solenoid is just loops of wire, okay? If we hold a magnet above this, group of loops of wire, we don't really get any current flowing through the wire, right? The wire is not hooked up to a battery. It's just sitting there hooked up to this measurement device that's going to tell us if there's a current flowing or not. Holding the magnet still does not show any current. But what the experiments in the 1830s showed is if you were to move this magnet up and down near the solenoid, a current spontaneously arose in the wire. So essentially, current from nothing, right? Current out of thin air. A current appeared in the wire, even though it's not hooked up to a battery, it's not hooked up to anything, all right, except a measurement device. So by pulling this magnetic object close to and farther away from this current carrying, or from this wire, allowed current to flow through it. So this current that appears is called an induced current, okay? And then the corresponding EMF or voltage required to cause this current is called the induced EMF. And so that's magnetic induction, okay? We're waving around a magnetic field and getting a current out of it. So we can do this experiment another way. Instead of using a magnet to change the magnetic flux, we could simply use another set of current carrying wires, okay? Hook it up to a battery so that current is flowing through those wires. And as you remember from the previous chapter, if the current is flowing in this direction, okay, counterclockwise, we're going to get a magnetic field pointing up. And so this is simply a source of another magnetic field. And if we were to bring this source of magnetic field close to or farther away from these set of coils, we still get a current. So it doesn't matter what is creating the field. As long as there's a field and it's changing with time near these sets of wires, you're going to get an induced current. So further experiments held this source of a magnetic field in place. And instead of moving it up and down, what they did is they installed a switch that basically interrupted the current and basically changing the di dt of the current. And what they again saw was another current in these wires being produced by simply changing the current through this solenoid, okay? So there is a couple of things happening, right? We are changing the magnetic field that is flowing through the center of this solenoid by changing the current. And that was producing the induced current. So if we can summarize this, these observations, if you have a loop of wire and you put it in a magnetic field and you don't change any aspect of that loop, you don't change any aspect of that field, you are not going to get an induced current, okay? No current will flow. If the magnetic field is constant, the shape and location and orientation of the coil do not change, okay? However, you do get an induced current if any of those quantities change with time. And so what that is leading us to, and I mentioned it already, is that a changing magnetic flux, okay, not just a changing field, but a changing magnetic flux produces an induced EMF, okay? So let's examine magnetic flux, B dot A. We can expand magnetic flux B dot A into BA cosine of the angle between B and A. And so basically, if we change any parameters of the flux with respect to time, so that could be one of three things. We could change either B with respect to time. We could change either the area with respect to time, or we could change the angle between B and A with respect to time. If any of those change with respect to time, we will get an induced EMF, okay? So what is causing this current and this voltage to appear out of thin air, if you will, is a changing magnetic flux. So a d phi b dt. Faraday's law states that the magnitude of this EMF that is created is equal to the change in flux with respect to time, okay? And I say magnitude, but you'll notice there's a minus sign here, okay? That minus sign is telling us that the EMF that's induced by the changing flux is induced in such a way to oppose the changing flux. We'll talk more about that minus sign in the next section. For now, let's focus on the magnitude of the EMF, which is simply d phi b dt. The units of magnetic flux, you may recall, is the Weber, or a Tesla meter squared. And if we're changing the flux with respect to time, right, by adding a factor of inverse seconds, well, that's actually equal to a voltage. So this is just another way, a Weber per second is another way to express the SI unit of voltage. Okay, so it's just interesting units analysis here. Let's do an example where we find the magnitude of that EMF, right? So what voltage is produced in the following example? So in example 29.1, we have a single loop of wire, and we've placed it in a magnetic field. Okay, the magnetic field is pointing up. And we see that the magnetic field is changing in magnitude, okay, at a rate of 0.02 Tesla per second. We're given the area of that loop, which is constant. Okay, the area is 120 centimeters squared, which comes out to be 0.012 meters squared. And then finally, we're told that the total circuit resistance, the circuit being made of this loop and the meter, the resistance of that is 5 ohms. So what do we need to do with this information? Find the induced EMF and the induced current in the circuit. And then part B, if the loop is replaced by an insulator, so if this yellow loop is replaced by an insulator, what would the induced EMF and induced current be? So let's tackle that. So obviously we're going to use Faraday's law, which states that the EMF, let's do the magnitude of the EMF, is going to be d phi b dt. Okay, so let me take this differential out and expand phi b. Well, we know phi b in terms of a magnitude of a dot product is BA cosine angle between B and A. And so we're given some of these parameters. We're not really given B, we're given d, b, dt. We're definitely given A, and we're not given cosine of that angle, but we can figure that out. Before I plug in some numbers, what I want to do is I want to apply the differential to only the parameters that are changing with time, which is B, right? So anything that's not changing with time is a constant with respect to that differential, and it can come out of the equation. So I'm going to pull out my A cosine phi. What I'm left with is dB dt. Now I can plug in some stuff. My area is 0.012 meters squared. My cosine phi. Phi is the angle between B and A. You'll notice that my area vector is parallel to B. The angle between them is 0. Cosine of 0 is 1. So we're going to have a number 1 for our cosine phi. And then finally, dB dt was given to us directly, 0.02 Tesla per second. Well, that's going to be the value of our EMF, right? Because the units of voltage can also be expressed as Tesla meters squared per second. That's an EMF. Multiply all these numbers together, and we will get the value of the EMF that's generated by this changing flux. 0.02 times 0.012 gives me a 0.24 millivolts, which is basically 0.24 times 10 to the minus 3 volts. So you get a little voltage out of that. And the second part of Part A is what's the induced current in the situation? Well, if the EMF is a voltage, then we know the resistance that the circuit has. We can find the induced current, right? The EMF is 0.24 millivolts. We know that V equals IR for any circuit that we're going to deal with in this course. And if V is 0.24 millivolts and the resistance of the circuit is 5 ohms, then the current that is induced will be 0.24 millivolts over 5 ohms, which comes out to be 0.048 milliamps. Okay, so a tiny little current. And so that's basically answering part A. Part B, what if this loop, you know, which comes out to a resistance of 5 ohms, what if we replace this loop with an insulator, something that has a very, very high resistance, for example, a piece of wood or bone, okay, something with a really high resistance. What will happen to the induced EMF and the induced current? Well, the induced EMF does not change. So why doesn't it change? Take a look at the equation that you use to determine the EMF. It does not factor in the object that is feeling this EMF, right? There is no R in here. There is nothing other than the area of that the object makes, right? Nothing involved that describes any properties of the wire. So the EMF doesn't change. But does the current change? Well, the current is given by V over R. So if R were to suddenly increase, then the current would certainly decrease, right? So if I were to stick a piece of wood there, and I was able to measure the EMF of the wood, I would still see 0.24 millivolts, but the current that EMF is providing an energy for, it's not enough to push it through a really high resistance. So the current that is a result is going to be very, very, very small, much smaller than 0.048 milliamps. So while the EMF doesn't change, the current should decrease. Well, it will decrease. It's no should, it will. Okay, I should decrease if we replace that coil with an insulator. All right. So now we kind of ignored the minus sign that was in Faraday's law. Let's talk about it. And let's look at some situations and kind of understand what the minus sign is doing. So the EMF that's generated in Faraday's law is generated such that it equals the negative of the change in flux. So the EMF that's created is created to oppose the change in flux. So if we want to figure out what direction that actually is, we need to first identify what is happening to the flux. So in this situation here, we have a loop of current, there's no current yet, right? We have a loop of wire, and we're going to apply a magnetic field out of that loop, and we're going to increase the magnetic field. What's happening to the flux? We're increasing the flux, okay? The flux is positive because it's pointing out the page. We're increasing the flux, and therefore the induced EMF will be negative. And so what does negative mean? Okay, well, negative means that if you use the right-hand rule to determine a current created by this B field in the picture, the current would be opposite to that right-hand rule. Okay, so in the picture you see a thumb, right, pointing in the direction of the B field. You curl your fingers around, you know, and that would give you a current flowing this way. But because there's a negative sign in Faraday's law, the actual induced current is opposing that one. So it would be this way, in the same direction as the EMF. Okay, so the induced EMF and the induced current would be opposite to the right-hand rule that would show you the current generated by this magnetic field. a little bit confusing. So I'm going to teach you a different way to analyze this, okay? The right-hand rule, instead of doing the right-hand rule on this, don't do that. We're going to do the right-hand rule on an induced magnetic field. So what is this induced magnetic field? Well, the induced magnetic field is going to be the magnetic field that's created to oppose the change in flux, okay? So if the flux is increasing out of the loop, the induced magnetic field that we need to oppose this increase is to add a field in the opposite direction, right? Think about adding vectors. If we have a vector pointing this way and it's getting bigger and bigger and we don't want it to get bigger anymore, we need to add a vector pointing 180 degrees away, right? A negative vector. We're going to add a negative to that to stop the increase. And now we're going to do the right-hand rule on B induced, and we don't have to flip anything. So if we put our thumb in the direction of, let me just try something here. If we put our thumb, oh, I didn't copy. Okay, I'm going to try this real quick. I want to copy this hand. We're going to do this. Yes. And then we're going to rotate it. We put our thumb in the direction of B induced. And what you're going to see is our fingers are going to curl around the clockwise direction, which is the direction of the induced EMF. Okay, so this is how we're going to think about this. To find the direction of the induced EMF, we need to first determine the direction of the induced magnetic field that opposes the change in flux. So let's take that idea and apply it to this situation. What if we have B pointing up, but its magnitude is decreasing? What field do we need to add to oppose that decrease? We should add another field in the same direction. Our B induced should be in the same direction as B so that we can oppose the change, which is a decrease. We don't want it to decrease anymore, so we need to add it back. We need to add some field back. The induced magnetic field will point in the direction of B if we're opposing a decrease. And so now our thumb is going to be in the direction of B. We're going to do the right-hand rule, and sure enough, our induced current, which is in the same direction as our induced EMF, will be clockwise. I'm sorry, counterclockwise. This is how clocks work. They go this way. Okay? So let's look at a third situation. Now B is pointing down and it's increasing. To oppose that increase, we're going to add a B field in the opposite direction. Okay? Our thumb will point up in the direction of B induced, and then our fingers will curl this way. And then finally, B is pointing down. It's also decreasing, so we don't want it to decrease anymore. We want to add an induced field to bring that decrease back under control. Our B induced will be that direction. And so we need to use our right-hand rule on B induced, which gives us a EMF in the clockwise direction, right? Clockwise. So what we just did, those examples there, is actually Lenz's law. But we did it without talking about Lenz's law. So I kind of already, brought you up to speed there. Because mainly trying to explain this without Lenz's law really doesn't make any sense. I don't know why the book did that, but I'm just, I go along with the book. So Faraday's law, let's go back to Faraday's law, right? Equals minus d phi b dt. We can actually increase, you know, as you saw before in the previous example, epsilon was small, right? The EMF induced was small. A way we can boost it up is by making n number of turns in this coil. So we can just, instead of having one coil, we'll have like a whole bunch of them. If we have n of them, then our EMF increases by a factor of n. Okay, and that's what this example talks about. While also adding a layer of complexity of having that loop tilted out of the field, okay? So that means we're going to have to include cosine theta into this. So this example, I'll let you guys, it's pretty straightforward. This example, I'll let you guys do it and just watch the video tutor solution, okay, just for the sake of time. So do this example. If you have any questions about it, you can actually, you know what I want to do together with this example is we're just going to work on the direction of the induced EMF, okay? I feel like the magnitude is pretty easy to calculate. Let's figure out what the direction is by applying the tricks that we looked at up here. So I want to paste that thumb real quick. Can I paste it again? Let me go copy it from up here. So, oops. Oh, okay. Let's copy this thumb. Okay. Just to get us ready to talk about the direction. I erased this 30 because I was thinking about doing the example and I wanted to erase the answer, but you know, you'll be able to figure this out, I'm confident. The direction, however, is a little bit trickier. So what we're looking at in this picture is we actually have a loop, 500 loops. And we're looking at the edge of the loops so that you can't really see the circle. The area of the loops is into the page such that the area vector is normal to it like this, okay? So we're gonna have either current flowing, you know, in and out here or vice versa, depending on its direction, okay? So that's what we're tasked with. What is the direction of the induced EMF and what's the direction of the current? In case you didn't already realize, the EMF direction is going to be in the same direction as the current. Okay, so if we're finding the direction of the EMF, that's also going to be the direction of the induced current. So let's start with that. So what's changing in this problem here? What aspect of the flux is changing with time? Is it the area? Is it the angle? Well, if we read the question, the aspect that's changing with time is going to be the magnitude of the B field. And so what direction is the B field? The B field is right here, going straight across, and its magnitude is decreasing with time. Okay, so that vector is getting smaller and smaller and smaller, okay? And so the EMF that's generated is going to be created by a magnetic field, a separate magnetic field that will oppose that change. So in order to oppose a decreasing magnetic field, right, we want to oppose this vector, this decrease in the vector pointing to the right. Well, the way we oppose it is we add another vector pointing also to the right. All right, if that vector, the blue vector, is getting smaller, we need to add another vector in the same direction to make it get bigger or to oppose the getting smaller. So our B induced is going to be pointing to the right. And so now we're going to point our thumb in that direction. And there we go. So our thumb will be in the direction of B induced. And when it is, you'll see that your fingers are curling out of the page on the top. Okay. Out of the page on the top and into the page on the bottom, right? So that is going to be the direction of our induced EMF or our induced current. Out of the page on the top, into the page on the bottom. Okay, and so if you go through the video tutor solution there, and you go to the end and it'll explain that. Okay, so do this problem, do the magnitude, and see if you come up with the same direction as in the answer key for that. So this is another example. We're not going to do this one either because what I want us to focus on is changing the flux with respect to time for B or A. And the third way you can change it is by changing the angle, but just for the sake of time, we can't cover everything. So we're gonna not worry about situations where the angle changes with time, okay? But it is a cool, it's a cool device. Well, it's more than cool. We use it everywhere. It's when we change the flux with respect to time and generate a voltage. This is a device called an alternator, which you may have heard of before, okay? It generates an EMF by changing the angle between B and A, okay? So B is constant, A is constant. The angle between B and A is what's changing with time. And so here you can see the circuit. It's created by this square loop, which obviously the loop is not changing its shape with time. The B field is constant, pointing to the right. And what is changing with time is this loop is allowed to spin, okay, while maintaining a closed circuit. It's allowed to spin, and so your angle phi is changing with time. And so this is generating a voltage. It's actually generating a time-dependent voltage, but it generates a voltage nonetheless simply by spinning a loop in a magnetic field. So it's a pretty cool application, but we're not going to study it in too much detail. The final situation that I do want to study in detail is going to be here, the slide wire generator. And what's happening in this is, well, we covered, right? We covered B changing with time. We covered the angle changing with time. So the final aspect of the flux that can change with time is the area, and that's exactly what's going on in this slide wire generator. So we will work on this example in the next video section, okay?